Here's video help for problem 9.1. It's 9.2 in the new edition. In all of this, I'll assume that you'll pay attention to the homework advice that's written to us, so I won't repeat things said there. We're taking a boxcar, a real important building block for so much of what we do, where this is 1 between these symmetric points and 0 everywhere else. We're going to take the Fourier transform of that. That's, of course, related to the signal due to a constant density for spins between minus and plus a half z0. Well, you know what will happen here. The integral here is really easy because this row being a rect means it's just 1 here and 0 elsewhere, so it'll just reduce the integration interval to minus a half z0 to plus half z0, and that's an integral that you can do really easily, and you can rearrange it and see that you have a sinc function, a sine of this over this, that same argument. And the neat thing about this is that you see it behave the way you expect. Because I've got these sharp corners, I get wiggles here. If this were really, really broad, in fact, go to infinity, then the denominator in the sinc function will kill it, except right at the origin, and it really approaches a delta function. I'm going to review delta functions in a minute. If you took, and squished this rect function into the center, then you'd end up broadening, doing the opposite in k-space. This, big in x space, small in k space, and vice versa. Well, what's interesting and what becomes a little bit more, a little trickier to do is the integral if you did the inverse. By the way, in my Fourier transforms, by putting in the 2 pi's here, you don't have to worry about the normalization. You don't have the 1 over 2 pi's or 1 over square root of 2 pi's and that sort of thing. And also just remember, I've got a minus sign for this Fourier transform and therefore a plus sign for the inverse. What about this integral? Well, you can actually just follow some of the steps outlined in the homework advice and just get it to a point where you can get an integral that you could read off or you find in an integral table or in Mathematica, or just Google it. Well, I'd like to tell you that you might have fun deriving it just from things that you know. If you remember delta functions and theta functions, if you don't, I'm going to review them for you. Here's a neat trick. I'm going to just talk about a toy here, and this is a building block. This is a fundamental little piece that you're going to find. I'm going to show you, I'm going to include in my notes that I send to you by email, I'm going to include the derivation, and so all you need to do is just try to understand it. To understand it, I think that you'll like to see a couple of the trees for the forest that you're going to see later. And if we understand these trees, it'll be easy for you. Here's my trick number 1. If I have an integral like this, I have, it looks like kind of a Fourier transform, right? But I have a 1 over k. Well, that actually, I'm not sure, how to do it. Well, I actually have complex variable ways of doing it, but nevertheless, from the start, I don't know what to do with this, but I do know what to do if it didn't have that k there. So let's take a derivative with respect to the external z that doesn't change in the integration, df dz, and I get I 2 pi k, I put the I 2 pi out, k, and that k cancels the k in the denominator, and now I have an integral that's famous. I know how to do that. That's the delta function. This thing here, dk with e to the I 2 pi k z minus z0 is delta of z minus 0, where the delta function, if you've never heard of it before, let me tell you, this thing is 0 if z is not 0, and it's some kind of infinity when z equals z0, such that the area under it is 1. One sort of tends to think about some kind of an area, well, heck, I've got it written down here, some kind of an area that you take the height to infinity as you make the width go to 0, but such that the area is fixed and equal to 1. So the integral, as long as you include this little peak, this infinite peak, will give you 1. Otherwise, it will give you 0. And so I just had z0 minus some small, but it could be any big number, a negative, z0 plus some positive number. Well, now I've got a simple statement. I know that the derivative of f, whatever it is, with respect to z, is I 2 pi times a delta function. And I know how to integrate a delta function. And delta function, when I integrate it, I just get a theta function. A theta function is just the simplest step function. 0 when z is less than z0, 1 when it's greater, for z minus z0 as an argument. And it just gives me a jump up. And sure enough, you see, the slope of that is infinite. And that's, of course, up to a constant. I can always add a constant in here. That constant you can argue away in this when you start using this later. Let's finally just check something. If I say to you that the derivative of this is that, well, let's check it. Does it obey the properties of a delta function? Namely, d dz of theta of z minus z0, is this thing going to behave like a delta function, the derivative? By the way, forget the derivative of the constant. Is it? Well, if of course, the derivative out here is 0, and the derivative is here is 0. So if I were integrating outside, not including this point, I'm going to get nothing. That checks. But if I integrate right over this step, from z0 minus epsilon to z0 plus epsilon, d dz of something, why, that's a perfect antiderivative. It's just that something at the upper limit minus something at the lower limit. Well, at the lower limit, it's theta at negative values. That's 0. Theta at positive values, that's 1. I get 1. It checks. I thought you'd enjoy working with these things and getting familiar with this thing, because delta functions and theta functions are important to us in things that we will be doing later on.